Hi friends, I am Dr. Adarsh Mangal, working as Assistant Professor, Department of Mathematics, Engineering College Ajmer. Today I will deliver a lecture on classification of linear partial differential equations of second order. Consider the differential equation of the type capital R into small r plus capital S into small s plus capital T small t plus function involving x, y, z, p, q equal to 0, where capital R, S and T are continuous functions of independent variables x and y possessing continuous partial derivatives. And here small r is del to u upon del x square, small s is del to u upon del x del y, small t is del to u upon del y square. Now the equation 1 will be hyperbolic if s square minus 4rt is more than 0, elliptic if s square minus 4rt less than 0, and parabolic if it is equal to 0. Now, if r, s and t are constants, then the nature of the differential equation 1 will be the same in the whole region, that is for all values of x and y. Let us take an example to illustrate the procedure. Classify the following differential equation: del to u upon del x square, del to u upon del x del y plus del to u upon del y square. It can be written as, in this standard notations, r plus s plus t equal to 0. If we compare this with the standard form, we have capital R is 1, capital S is 1, capital T is 1. Therefore, s square minus 4rt becomes minus 3, which is negative. So that we can say the given differential equation is an elliptic partial differential equation, because s square minus 4rt less than 0 means elliptic equation. Now, if r, s and t are functions of x and y, earlier we have seen that r, s and t are constants. Now we are supposing the functions of x and y. Then the nature of the differential equation will not be the same in the whole region. It depends upon the condition obtained after putting the values in s square minus 4rt. The equation will be hyperbolic if s square minus 4rt is more than 0, elliptic if it is less than 0, and parabolic if it is 0. Now let us take an example. In this case, classify the following differential equation: del to u upon del x square plus x del to u upon del x del y plus y del to u upon del y square. If we compare this with the standard equation, then we have r is equal to 1, s is equal to x, and t is equal to y. Therefore, s square minus 4rt becomes x square minus 4y. Hence, the given partial differential equation will be hyperbolic if x square minus 4y more than 0, or we can say that x square more than 4y. Parabolic if x square minus 4y equal to 0, or x square is equal to 4y, and similarly in the case of elliptic. Now, let us consider the linear partial differential equation of second order in n independent variables x1, x2, x3 up to xn by the following manner: double summation I is running from 1, j is running from 1, aij del to u upon del x I del x j plus summation I is running from 1 to n bi del u upon del x I plus cu equal to 0. This is a standard form where aij, bi and c are constants or functions of independent variables x1, x2, x3 up to xn, and independent variables we are considering this. In this, let phi be an operator defined as summation, double summation I is running from 1 to n, j is running from 1 to n, aij del I del j. Now the equation 3 will be elliptic. Equation 3 means standard equation. If phi is positive for all real values of del I and it reduces to 0 only when all del i's are 0. Parabolic, if the determinant vanishes, determinant from the equation a11, a12, a13 from the coefficient, that is 0. Hyperbolic, if phi can be both positive or may be negative. Sometimes it may be positive, sometimes it may be negative. If the coefficients are functions of independent variables 1, 2, 3 up to n, x1, x2, x3 up to xn, then the same differential equation can be elliptic, parabolic and hyperbolic at different points. And if coefficients are constants, then the equation will have the same nature throughout. Now let us take example. Classify the following differential equation: del 2u upon del x square, del 2u upon del y square is equal to del u upon del z. Equation can be rewritten as standard equation, which we have stated over here. I is running from 1 to n, j is running from 1 to n, aij and so on. It can be expanded like it. A11 del 2u upon del x square, A22 del 2u upon del y square, A33 del 2u upon del z square plus A12 del 2u upon del x del y, A23 del 2u upon del y del z and so on, plus B1 del u upon del x, B2 del u upon del y and so on, plus c equal to 0. If we compare first equation with the second, we get A11 is 1, A22 is 1, A33 becomes 0, A12, A13, A21, A23, A31, A32 all are 0. Now, if we form a determinant like that, A11, A22, A33, diagonal elements, A12, A13, A21, A22, by putting the values we have 0. Determinant vanishes. If determinant vanishes, then the point B is stated, determinant vanishes, then the equation is parabolic. So that the conclusion is, hence the equation is parabolic. Another example, classify the following differential equation: del 2u upon del x square, del 2u upon del y square is equal to del 2u upon del z square. If we compare the equation with the standard equation, we have A11 is 1, A22 is 1, A33 is minus 1, remaining the coefficients are 0. So that determinant is non-zero. If it is non-zero, then we have to frame a operator phi, that is double summation aij del I del j. If we expand this, then we have A11 del 1 square, A22 del 2 square, A33 del 3 square, A12 del 1 del 2, A21 del 2 del 1, A13 del 1 del 3, A31 del 3 del 1, A32 del 3 del 2. By putting all the coefficients stated over here in the phi, we have phi is del 1 square plus del 2 square minus del 3 square, which indicates that if del 1 square plus del 2 square more than del 3 square, then phi becomes positive. And on the contrary, if del 1 square plus del 2 square is less than del 3 square, then phi becomes negative, which is indefinite. Sometimes it may be positive and sometimes it may be negative. So the point C, if phi can be both positive or negative, the equation will be hyperbolic. Hence the conclusion is, equation is hyperbolic. Now another example, classify the following differential equation: del 2u upon del x square plus 2 del 2u upon del y square plus del 2u upon del z square is equal to twice del 2u upon del x del y plus twice del 2u upon del y del z. Comparing this with standard form, we have A11 is 1, A22 is 2, A33 is 1, A12 is minus 2, A13, A21 0, a31, a32 0 and a23 is minus 2. So that here determinant is non-zero. Again we have to come on phi operator, and if we put the values of the coefficient stated over here, then we have phi is equal to del 1 square plus 2 del 2 square plus del 3 square minus 2 del 1 del 2 minus 2 del 2 del 3. On solving it, we have del 1 square minus 2 del 1 del 2 plus del 2 square, that is del 1 minus del 2 square, and similarly del 2 minus del 3 square. Here del 1, del 2, del 3 may be positive, may be negative, but they present in the form of a square, so that phi becomes definite positive for all values of del 1, del 2 and del 3. It means the given equation is an elliptic differential equation, because point A is phi is positive for all real values of del I. Hence the equation is an elliptic differential equation. Thanks for being with me.